Hey everyone, in this video, so we have a chain of length L. This is its linear mass density of rho. This capital M is the total mass of the chain. The L is the total length of the chain, okay? So just to establish that, we need to find a y of t, a function of time, which will tell us, when we give it a time, it'll tell us the length of the chain that's hanging over an edge, which I haven't even established yet. So anyway, this chain is hanging on a horizontal plane, a surface, frictionless, so no friction, no, it's a big no. So no friction at all. A little small portion of the chain is going to be hanging over the edge, the same edge that I had mentioned and drew. And this little length of the chain we're going to call y naught, because why not, right? Anyway, so times 0, the length of the chain that's hanging over the edge, because we need a little bit of the length, a little bit of the chain to hang over the edge in order to initiate the motion, because it's frictionless, so it means as soon as a little bit's over the edge, it's going to go slowly and exponentially increase in speed and end up all the way down. Anyway, so let's talk about this little piece that's hanging over the edge. It has a mass. We call it little m. Little m is going to be rho times y. What is rho? Big M over big L. And the y is still there. A little bit more intuitive way to look at this would be y over L times big M. Y is a small number. It's less than L, obviously, because it's just hanging over the edge at any time, right? So like y is less than or equal to L, right? Because as soon as y is L, then it's 1, and little m is essentially the total mass of the chain. So yeah, as I was saying, okay, so another thing I forgot to establish, we're going to take y to be positive as it's going down. Positive. It's very important. Okay, so yeah, as I was saying, the y is going to be a smaller number than L, so you're going to get a small number here that's modulating this m, so this mass, right? Because it can never exceed the total mass of the chain. So we have this expression, and let's talk about the force is acting on the chain, which is the force of gravity, which is mg, which is g, but we have an m, right? Because it's a force in joules. So it needs a mass and an acceleration. This we equate to big M times A. We isolate for the acceleration A. We get little m over the large M. And then, yeah, there's a G here too, this G. Yeah. Anyway, we have a small m, so we have an expression for the small m here. We will substitute into here and effectively reach this expression, which is m over L times 1 over m, big M, big M. I guess there's no little m's because they're gone. G times y. So as soon as you take this, put it into this little m, this is where you get. It's a multiplication, so these m's will cancel. One on top, one on the bottom, obviously. We're left with, let's take it up here. We're left with g times y over L. G, y over L. Let's do, this is equal to g over L times y, right? Here's what we're going to do. This is, it's still A, it's still the acceleration. So acceleration equals this, equals this, equals this, equals this, equals acceleration. What is acceleration? The second time derivative of y of t, as we all know. Yeah. So now, here's what we're going to do. I'm just going to rewrite this again. G over L times y. We're going to call G over L, this thing, this expression here, alpha squared, and you'll see why. So this means it's equal to alpha squared times y. This is a differential equation with solution of the form, let's take it up here. This is, okay, I'll just do it here. The solution to this, so the y of t that we need in order to reach this expression, it's a differential, is going to be of the form a, which is a constant, times an exponential to the power of alpha t, plus b, which is another exponential, or another constant, times the exponential to the negative alpha t again. Okay? This is incorrect. This is not an equal sign. We could say that this leads to that. So of solution of the form, there we go, of this form, okay? So this does not equal that, just make sure, okay? Let's do this. Anyway, this is equal to y of t. So we know already because it has to be of this form. We don't know what a and b are. Yeah. Well, let's find out what they are, right? So we have y of t. I'll just do it here. Y of t equals to a exponential alpha t plus b exponential negative alpha t. There's a negative here, it's very important. Differentiating once. We get an alpha, a common alpha term outside of the expression. We still have the a's and b's. However, we acquire a negative in the midst of these two, in the middle of them. There's a negative now because when you differentiate an exponential, you multiply by anyway, so you get a negative out of the exponent of the exponential function of e. So this b catches a negative. So here's where we think about it a bit, and we think, sorry, excuse me. Y dot of t is the velocity, okay, of the particle, of the object, of the chain. So when you differentiate it once, it's going to be the velocity. We know in the beginning it's not moving at all, it's just hanging out. So we know that y of 0, y dot of 0 equals 0. Okay, so we put in, let's put in a 0 for, just get rid of this quickly, guys. We put in a 0 in all the t's in this expression. This goes to 1, this goes to 1, we're left with equals to 0 equals to alpha a times 1 minus b times 1 equals to 0. Again, it's the same thing. Anyway, we divide both sides by alpha. 0 divided by alpha is 0. From this, a equals b, right? Because a times 1 is a minus b times 1 is b. You move the b over to this side, you get a equals b. This is a very important relationship that we're going to use right away. So we know this. We can rewrite our solution that we haven't, I guess we haven't wrapped it up yet. Like there's still a couple more components that we need. But we know that a equals b, so, or b equals a, so you can either use the b, bb, or aa, it doesn't matter. We're going to use a, so we take the a outside of the brackets, plus b, no b here, minus alpha t. This equals to y of t, so we're almost there, almost at our y of t that we need. Now let's work with a. We know another thing, right? We know that in the beginning, times 0, we have a little bit of the chain hanging. We call that y naught, okay? This y naught is arbitrary. You could have a little bit or a lot of bit of the chain hanging. It's up to you, really. So all of these, anyway, I'm just going to work with the variables. I won't touch any numbers. So we know that at time 0 equals to y naught. So this same y of t, let's put in a 0 for t. What do we get? Y of 0 equals 2. So you put in a 0 in for t here, and for t here, these go to 1, 1, 1 again, as they did here. Yeah. Essentially you get a, 1 plus 1 equals to 2a equals to y of 0, which is not y dot of 0. So it's important to make that distinction. 2a equals to y of 0, which is y naught. Let's rearrange this. Y naught, a equals y naught over 2 plus y naught. Already made that joke. Let's plug in this expression for a instead of a in our solution. We get y naught over 2 times e alpha t minus e negative alpha t. This looks awfully a lot like y naught over, I'll just rewrite it. I guess, okay, cool. Anyway, so these exponentials look, a little bit suspicious. Because if there's a 2 underneath here, well, it was already equal to that, but it's a little more intuitive this way, like you can see it visually. This is the hyperbolic cosine of alpha t. And this is the solution to this problem. So you put in a t, you get a length in meters, or in however you established it, of the portion of the chain that is hanging over the edge at that time, right? So you'll have to,